define what we mean by a finite dimensional operator. Finite dimensional are finitely approximable operator. And our definition was pretty simple. That imagine you have two normed spaces, E and F, and you have an operator A from E into F, where E and F are just normed spaces, okay, nothing more. Then A is called finite dimensional or finitely approximable. Finitely approximable if what? If you compute the range of A, okay, so it turns out to be finite dimensional. So if the range of A is a finite dimensional, in other words, you can find some vector which can span this whole of the range, which can serve as the basis of the range A, then we can call an operator as a finitely approximable operator. And then we denoted the space of all finitely approximable operator from E into F by this subspace, okay? And we actually showed, we can see that this space is this is a closed subspace of. So it's a closed subspace of the space of all linear bounded operator from E into F. Okay? And then we talked about one example of finitely approximable operator, and that example was that every Hilbert-Schmidt operator. Okay. So every Hilbert-Schmidt operator is finitely approximable. Okay. So I would like to begin today with a result, okay, which help us to approximate another kind of an operator, which we call as compact operator. You're going to see that there is a relationship between compact operators and finitely approximable operators up to date. So I would like to prove something not too much unusual. We have done some version of it already in real analysis. Okay, so we say that let E and F be Banach spaces. So imagine that you have two Banach spaces, and let A be an operator from E into F, which is finitely approximable. No, I think I'm saying something silly, very silly. Yes. This is the definition of finite dimensional operator. Okay? But what we mean by a finitely approximable operator, so it's a one step ahead. It says that so A from E to F is called finitely approximable if there exists a sequence of finite dimensional operators. Yes, there exists a sequence of finite dimensional operators such that this sequence approximates the given operator A in operator norm. Okay. This goes to 0 as n goes to infinity. Okay. So what's a finite dimensional operator? If the range is finite. What is a finitely approximable operator? If you can find a sequence of finite dimensional operators that can approximate your given operator, then you call that operator as finitely approximable operator. Okay? And every Hilbert space is finitely approximable. We saw that because we saw that the kernel of a Hilbert-Schmidt operator can be approximated by the kernels of finite dimensional operators actually, and hence the operator itself can be approximated by the sequence of finite dimensional integral operators actually. So we saw this last time actually. So we did some silly mistake and we corrected it. Okay, so what's the theorem? The theorem says that imagine you have two Banach spaces, like complete normal spaces, and I have an operator, which is an operator from E to F, and it's a finitely approximable operator. Okay, finitely approximable. Finitely approximable operator. Okay. And let Fn is in N be a bounded sequence. A bounded sequence. So if I have two Banach spaces, an operator which is finitely approximable and a bounded sequence, then if you have this setup, then when A would be operated onto this bounded sequence, okay, obviously is going to be a sequence in F, okay, then this sequence has a convergent subsequence. Convergent subsequence. Okay? So if we have a finitely approximate operator and we operate into a bounded sequence, then this, what you call the range of the sequence under the finitely approximable operator contains a convergent subsequence. But this is true when E and F are Banach spaces, not in general. Okay? So what we are going to do, we are going to run so-called the diagonal argument. So here's a proof. Let's play the pivotal proof and defining the compact operators. So the first case is that if A itself is a finite dimensional operator, okay, so if A is itself a finite dimensional operator, why a finite dimensional operator must be finitely approximable?
It's self-sequence.
Okay, just take a constant sequence. So it's like just take an to be A itself, then obviously this now would go to 0 as it goes. So finite dimensional operators are, you know, finitely approximable. So consider the case if A is finite dimensional. Okay. So if A is finite dimensional, then what? A range of A is finite, okay, and let's say what we can say about this AFN actually. So every finite dimensional operator must be bounded actually. It must be bounded. We know that, that if you have an operator between two finite dimensional spaces, which the range is at least finite dimensional, okay, then it must be bounded actually. Okay, we have done this several times in our course. Then AFN is bounded. Then if the AFN is bounded, okay, then we have this beautiful result. Okay, what is the result that gives you? So you have Bolzano-Weierstrass theorem actually. Okay, so AFN is bounded, and hence by Bolzano-Weierstrass. Okay, Weierstrass theorem. So what was the statement of Bolzano-Weierstrass theorem? That if you have a bounded sequence, okay, and it's also true in Rn actually. So it's not necessarily true in R, but it's also true in Rn. So what we did was a result that was, in R actually, but you can generalize it to Rn actually. So it says that if you have a bounded sequence, then it must have a convergent subsequence. Okay. AFN, where n is in N, must have a convergent subsequence. So everything is fine actually if itself is finite dimensional. The second case would be in the, so this was a bit trivial actually, but it's worth mentioning, okay, trivial things. If A is not finite dimensional, so then it's finitely approximable actually. Okay? So if A is finitely approximable, next is what do you call the more general case when A is any operator between P to F, where it's finitely approximable. If it is finitely approximable, it's going to be a bit trickier, not going to be as straightforward as it appears actually. But yes, there is going to be rule, finitely approximable. So if it is finitely approximable, there must be a sequence of finite dimensional operators. Okay? Finite dimensional operators. There exists a sequence of operators such that the range of A and B is finite dimensional. Okay, such that the norm of A and the difference of A and AN in the operator norm, in other words, this norm L from E into F goes to 0 as M goes to. Okay, so this is what that is going to be true. Now, what we like to do, we like to essentially is this actually. So take the original sequence. Okay. Take the original sequence. So what else is given to me? It is also given to me that Fn is a bounded sequence actually. Okay. So take this original sequence. So take Fn, and n is an n, the it's a bounded sequence. Better is to say let be a bounded sequence as mentioned in hypothesis. Okay. And pick a subsequence of it. And pick a subsequence of it such that, okay, so imagine I have a subsequence of it f11, f12, f13, such that, so it's a kind of a subsequence which is convergent under the f1, is a1 actually. Okay, so a1 fn is convergent to some g1. So what I'm saying is that imagine I have a subsequence, this bounded sequence, and I'm operating a1 onto it actually. So if I'm operating a1 onto it, it must be a bounded sequence. And if it is a bounded sequence, it must contain a convergent subsequence actually. So I'm saying that, okay, take the sequence, operate a1 onto it, subsequence, operate a1 onto it, and it converges to what you call g1.
Sir, convergence is bounded to g1.
Yeah, sir?
Convergence कैसे apply होगा?
First case actually. Okay. So a1 is what? A1 is a finite dimensional operator. So when it is going to operate it on the original sequence actually, will be on some suitable subsequence of the original sequence, which will be itself, okay, and it's converging to what you call some g1. Okay.
वो जो f1 f2 f3 वो जो सीक्वेंस है वो e में है और e फाइनाइट डायमेंशन में लास्ट में तो नहीं है.
Then only finite dimension now, but a1 is finite dimensional. So the range of a1 is going to be finite dimensional, and hence when this is operated onto fn is going to give you the subsequence such that convert this to.
Sir, ये f sub 1 n है जो.
So it's a
notation है ना
subsequence.
सिर्फ.
Huh?
f1n.
Yeah, it's a notation actually. It's just a notation actually.
Just so that a1 should be applied.
Yeah. Okay, it's just a notation. Okay. And similarly, let's take another sequence, subsequence. So it's like that's a subsequence for a1, in other words, such that a1 fn is converted to some g1, but you can also take a subsequence for
f2
f22, f23, so on and so forth, such that a2 or 2n that's convergent to g2 actually.
Sir, वो दोनों express तुरंत fn पे apply हो रहा है या a fn पे? क्योंकि दोनों bounded हैं.
So I'm saying that take this is fn and I'm rephrasing its elements in this manner, and then I'm operating a1 onto this rephrased version of sequence. Okay, and I'm saying that this is, since finite dimensional, it must converge actually, so it must be bounded and hence convergent, and it must be convergent to g1. So this is the same sequence in disguise. Okay, this is what we call the same sequence in disguise. Okay, almost or maybe some chosen terms of the same sequence in such a way that this a1 and a2 they are convergent. Okay, and in the similar manner, what I can do that I can fk1, fk2, fk3 in such a way that ak and fkn, what do you call gk. Okay. And I'm saying that now these terms, so that the diagonal terms, diagonal sequence that you get out of it is an interesting sequence actually. We're going to play with it. Okay? We're going to play with it and we'll try to find a subsequence which is kind of, which has the required property, which has a convergent subsequence. Okay? Now, consider this sequence which is f and n actually. So it's like a diagonal sequence where n is in n. So what would be the relationship between this subsequence, okay, and all these subsequences? Would there be any relationship? So I'm saying that
the elements of
the elements are, if you wish, you can treat also this as a subsequence of all these subsequences actually. So that's a pretty interesting kind of a subsequence, which is subsequence of all these subsequences. Why this would be the case?
So एक एलिमेंट है ना
सर हर एक से एक क्रम कोइंसाइड कर रहा है.
Yes. Mm-hmm. Why this would be a subsequence? So give me a subsequence of 1 over n.
not
Okay. So just to make it. So imagine that I have this actually, one subsequence. 1/2, 1/3, no, 1/4, 1/6, and so on and so forth. And I have another subsequence. 1/3, 1/6, and 1/9, and so on and so forth. Okay? And then I pick this sequence actually. Okay? So the diagonal, what do you call? Just like a 1/2 and 1/6. Can I treat this sequence as the subsequence of all these sequences?
No, they're not taken one.
So second one is an
पहली
A.
भी तो है, फर्स्ट वाले भी तो है.
सर सारी सब सीक्वेंस को एक सीक्वेंस बना दे फिर बनेगी सीक्वेंस.
What do you mean by-
सारी जो रोज हैं हमारी
Uh-huh,
सब रोज को हम क्लिक करके एक सीक्वेंस बना दो.
uh-huh.
फिर उसकी हम कह सकते हैं कि पेन इज सीक्वेंस
Yes,
सबसीक्वेंस.
yes, yes. It's a good point. It's a good point. So in other words, if I treat, can I? Okay.
So शायद यहाँ पे वही काम कर
तो वर्ड एंड रिप्लेस यही पॉइंट आर सा.
में यही कर रहे हैं जो आपने कहा.
नहीं ऐसा नहीं.
It's treating the sequence of, so
All
it's
the
treating
terms.
f and n as the sequence of all these subsequences, like if you put them in a one sequence. actually. Okay. So in other words, so consider f and n, okay, and one sequence would be like, okay, the one term in the sequence would be repeated actually. So if I have f11 and f11 and f11,
सर हमने नोटेशन लिखी है इसमें तो लिखी नहीं हुआ. सर ये चूज किस तरह से किए हैं हमने?
what do you mean by?
ये जो
So diagonally choose again. So
नहीं जो पहली सीक्वेंस है, सेकंड है वो फर्स्ट सब सीक्वेंस की सब सीक्वेंस है, इसी तरह से चूज किया. हाँ.
find missing actually, that so if we have this subsequence such that A1, F1 and converges to G1. So the next sequence is the subsequence of the above sequence such that this A2 to Fn is converging to what you call G2. This point was missing, and so on and so forth. So what we are doing is that okay, you have subsequence within subsequence and within subsequence and within subsequence actually. So it's like a subsequence of subsequence of subsequence of subsequence. And then I'm saying that okay, take this what do you call diagonal element, and then this would be the subsequence of every subsequence actually. Okay, so consider f and n such that what? Such that its subsequence is a subsequence of f k n actually. Okay, where n is bigger than or equal to k. All right, and if this is the case, then if I take an operator which is what we call AM and I write it on the suitable so what can I say consequently? That if I take so if I take this sequence, okay, which is f and n, and I operate the operator am onto it actually. So what result you would expect? Okay, so by definition it follows that, by construction it follows that this must converge to the GF. Okay, and this is true for every m in n. So now we have found a subsequence of the original bounded sequence which is converging under every single element of the sequence of operators which are approximating your original operators. Okay? And now we can say that, okay, using this sequence, we can get what we want. We can get what we want. Okay? What I'm going to show, the next is my claim that this, so when you take this subsequence, this diagonal subsequence, and operate it on, what do you call it, and operate A onto it, then this is a convergent, actually, and hence this would be a convergent subsequence of the original sequence. Okay, this is what that will have to essentially do. And in order to show this convergence, it is sufficient to show that it must be Cauchy actually, because E and F both are complete actually. Okay. So consider this calculation, which is that you have FA, Fn minus A operated upon the Fn. Okay? And I'm saying that, okay, I can estimate this by adding, subtracting something, and that something would be, okay, this, using triangle inequality, we're going to get A Fn minus AK, okay, the K is any number, right, between natural, so it's like it's a term in the given sequence.
Of operators.
Of the operators, finite dimensional operators which are approximating your A. Okay? A F N N plus k fmm plus